Well, would you like to see another example of finding relative extrema and saddle points?
Certainly.
Well, I'm glad to hear that. So here's our function. G of xy is just x times y. The partial with respect to x is y. The partial with respect to y is x. And both are 0 at the point 0, 0, 0. And that's the only critical point, because all these derivatives are nicely defined and exist and are 0 at this point, and that's the only spot. Notice that the second partial of this one is 0 with respect to x. The second partial of this one with respect to x also 0. But g of xy, the mixed partial of this with respect to y is 1. The partial of this with respect to x is 1. So either way we do that, that's 1. So we have the second partial with respect to x 0 times the second partial with respect to y 0 minus 1 squared, so that's a negative number. So the point 0, 0, 0 is a saddle point. Going back to our theorem, see, when this happens, it's a saddle point. So it's a saddle point, and now I can show you what that looks like with a saddle point. And I really am liking the format a little better if I fill the surface. Oops, sorry, I didn't mean to fill it with that. I meant to fill it with the color map. There we go. So yeah, the point where x is 0 and y is 0 is a saddle point. Here's x 0, here's y 0, and right here in the middle, see, it's a minimum this way and it's a maximum this way. So there's a saddle point. You understand that?
Certainly.
Great.